Hi everybody. Today we continue our discussion of ideal gases and the law of conservation of energy as it's understood in thermodynamics. And first I would like to start by discussing problem number 339. So it says, will the energy of the air in a room increase if a stove is heated in it? So we have a room and a stove in it, and the room is heated and the temperature in the room is increasing. And the question is, will the energy of air contained in this room increase together with the temperature? So if we assume that the room temperature is described by a law of ideal gas, then we must write the gas pressure times the room volume means the mass of the air over some mean molar mass, universal gas constant, and absolute temperature. That is the law of ideal gas, and it certainly applies in any situation whenever we have anything, any process with the ideal gas. And so this equation describes the air in the room. This is the pressure in the room. The pressure is defined by the atmospheric pressure outside the house, outside the building. The pressure is always equalized outside and inside the building. So the pressure is given, actually it's 1 atmosphere, and it's defined by the outside surroundings of the building, by the outside atmosphere. The pressure is constant. It does not change during this process. The room volume is also constant. Obviously, the room is not changing its volume. So all this is constant. But we know that the temperature inside the room is rising. We increase the temperature of the air. How can it be so that this is constant and the temperature is increasing? If we look at this equation, we understand that everything here is constant. The universal gas constant doesn't change, the molar mass doesn't change, and the only thing that can change together with temperature is the mass. The mass of the air contained in the room. And as we have established that the pressure inside the room and the room volume remain constant, therefore, from here we must conclude that the product of mass of air inside the room and the temperature of air in this particular process remains constant. It means that when the temperature is increased, the mass of air in the room is decreased. Why so? It's easy to understand, because if the temperature is increased, the gas wants to expand. It wants to increase its volume. But the room volume is closed and it's constant. So the gas will leak out of the room through all the slits and cracks, and so the mass will go out from the room. The air will somehow leak to the street. And so the mass of air contained in the room will decrease if the temperature will increase, so that the product of mass times temperature remains constant. Because there are actually many slits in the window, slits under the door, and the air in the room may easily go out. if it's heated. So from the conditions of this problem, we understand that if the pressure is atmospheric pressure and remains constant, and the room volume remains constant, then necessarily this product remains constant. What can it give us as far as the total energy of air in the room is concerned? If we talk about the energy of gas, we must remember that the mean kinetic energy of one molecule of monatomic gas is 3/2 kT. We derived this expression, this relationship, when we obtained this relationship when we derived the ideal gas law. So this is the mean kinetic energy of one molecule. For monatomic gas, if the gas is not monatomic, then the coefficient will be different. If there are two atoms in a molecule or 3 atoms in a molecule, then this coefficient will be different. But anyway, the energy of a single molecule will remain proportional to temperature. So there will be some coefficient, well, let it be A times kT. Some coefficient which, in case of monatomic gas, is equal to 3/2 if the molecule consists of 1 atom, but it will be different constant if the molecule of the gas consists of a different number of atoms, like 2 or 3 or more. So anyway, the mean kinetic energy will be proportional to the gas temperature. If we multiply this equation by Avogadro constant, then remembering that Avogadro constant is the number of molecules in 1 mole, then, and this is the kinetic energy of 1 molecule, then this expression will give us the total kinetic energy in a single mole of ideal gas. And if we now multiply it by a number of moles, then that will be number of moles contained in the room, then this total expression will give us the total energy of ideal gas inside the room. That is what we have to find in this problem. In order to find the total energy of all the molecules, all the gas inside the room, we started from a kinetic energy of a single molecule, and then we multiplied it by an Avogadro constant and obtained the kinetic energy of molecules inside a single mole, and then we multiplied this quantity by the number of moles in the room, and we obtained total kinetic energy of all the gas in the room. And now, remembering that nu equals exactly this coefficient, the mass over molar weight, we understand that if the mass changes, like actually in our case, if the mass of air changes, then the number of moles inside the room changes. So the changing mass and the changing number nu are related here. But anyway, this is the total energy, and the total energy of gas inside the room can be denoted by a capital U. Total internal energy of ideal gas inside the room. So, from the above, we have concluded that this expression is constant, regardless of the fact that temperature is increasing. It remains constant because while temperature is increasing, the mass of air in the room is decreasing. And the same is here. While temperature is increasing, the number of moles will be decreasing. And so if we remember that this is exactly the number of moles, yes, and we recall that universal gas constant is just equal to Boltzmann constant times Avogadro constant, then we can write from this expression that all this will be A. Then Boltzmann constant times Avogadro constant will give us universal gas constant and temperature and the number of moles. And this expression RT, the number of moles, equals to P times V, pressure times volume. So what we obtain here is some constant, pressure times volume. And we know that pressure times volume in our particular process, when the air inside the room is heated, this expression remains constant. So looking at this line of formulas, we understand that the total internal energy of ideal gas inside the room will remain constant as the room air is heated. As we increase the temperature inside the room, the total energy of the air inside the room will remain constant. It means that when heating the room air, when increasing the temperature in the room, we don't increase the energy contained in this room. Where does the energy of the heater go? The energy of the heater in this case is spent not to increase the energy of atmosphere inside the room. The energy of the heater goes to increase the energy of the outside air, of the atmosphere of the Earth. So when you heat the room, when you switch on the heater, when you want to increase the temperature inside the room, you actually increase the energy not inside the room, but in the outside atmosphere, because the hot air leaks out of the room in order to keep the pressure constant and equal to 1 atmosphere. And because the room volume is constant and the pressure is constant, and due to these laws of ideal gas, we may conclude that when you heat the room, you actually supply energy to the outside atmosphere surrounding the building. You don't increase the energy inside the building, the energy of atmosphere. So this is a simple but interesting conclusion. And now let me proceed with problem 371. Problems 371. That's it. By the way, the day after tomorrow, all my students will have a distant written test. That is on Saturday morning at 10 o'clock Moscow time. All the instructions needed I will send you tomorrow night. Tomorrow, Friday, by the end of the day, by the end of the working day, I will send you the necessary instructions how could you take the written test on Saturday. That is to those students who study distantly. And now we consider problem number 371. When a small ice crystal is placed into overcooled water, it begins to freeze immediately. it begins to freeze, the water begins to freeze instantaneously, as it says here in this problem. And the question is, what amount of ice is formed from 1 kilogram of water overcooled to -8 degrees Celsius? So we have the mass of water, 1 kilogram, at temperature -8 degrees Celsius. It should be noted that when you have water, when you have some water and you cool it down to 0 degrees Celsius, this water usually begins to freeze, and the frozen water is ice. So you obtain ice if you try to cool the water down below 0 degrees centigrade. But actually, the freezing of water occurs on some impurities, on some around some atoms of other substances which are always found in water. But if this amount of water is pure and if it contains no contaminations, the pure water can be cooled down below 0 if you do it slowly and carefully without adding any impurities and imperfections in this water. The water can be cooled below 0 and it will remain liquid. But in this case, you can decrease the temperature of water to -8, to -15 degrees, etc. But if any imperfection is added to water, any external particle is added to such overcooled water, then it immediately starts to freeze around this particle. So you have a liter of water, and it remains water at low temperature. Such water is called overcooled water, and it remains liquid. But if anything is added here, for example, a small crystal of ice is just thrown into this water, overcooled water, a small crystal of ice, then all the water around ice is starting to freeze immediately, and you obtain such a lump of ice here which grows quickly. And the question is, in this problem, how much ice is formed from 1 kilogram of water overcooled to -8 degrees Celsius. What amount of ice, or what will be the mass of ice? So this is ice, and the mass of ice will be denoted by Mi. So in this problem, we need to find the mass of ice. Probably all the water will turn into ice. I don't know. We have to analyze it. All the water may turn into ice. Sometimes it happens. But it's also possible that only part of water will turn into ice, will freeze. Only some part of water. And the other part will remain liquid. This is also possible. So we have to analyze this situation. And in order to analyze it, we have to recall that the specific heat of melting of water, or specific heat of melting of ice, is approximately 80 calories per gram. So if 1 gram of ice melts into water, you have to, in order to melt 1 gram of ice, you have to supply it with 80 calories of energy, of heat energy. So if you want to melt some ice, you have to supply energy. But if water is freezing, this energy is released. The process is reversed in time, and so the energy is released by freezing water. So 80 calories of heat energy will be released if 1 gram of water is turned into ice. That's what we must understand. So if all the water in the amount of 1 kilogram is turned into ice, then the amount of energy, the amount of heat energy released will be what? The amount of heat energy released if 1 gram of water is turned into ice times the mass of water in grams. So that will be the total amount of released energy if all the water is turned into ice. So that will be 80 calories per gram times the mass of water. It's given as 1 kilogram, so we need to take it to convert it into grams in order to cancel the grams here and here. So what we obtain is 80,000 calories. That's the amount of heat that will be released if all the water turns into ice. If 1 kilogram, 1,000 grams of water turns into ice, then this amount of energy will be released, 80,000 calories of heat energy. But the initial temperature of water is minus 8 degrees. So where do you think this amount of heat energy will go? Obviously, as this heat energy is released inside the water, it will go first of all to heat the water. And the water will be heated up to 0 degrees and probably not to 0 degrees. Maybe it will be heated just a few degrees. How can we understand it? How much will be the increase of temperature of water? So in order to assess this process of heating water, let's calculate the amount of heat needed to increase the temperature of water from minus 8 up to 0 degrees centigrade. So that was the amount of heat released if all the water is turned into ice. And that will be the amount of heat delta Q2, the amount of heat that we need to heat the water, to increase the water temperature up to 0 degrees Celsius. So this amount of heat can be calculated if we know the specific heat of water times the mass of water times the temperature difference. The specific heat of water in calories is just 1 calorie per gram per Kelvin, degree of Kelvin. The mass of water is 1,000 grams. And the temperature difference we are interested in is 8 degrees, because we discussed the possibility of heating water from minus 8 up to 0 degrees Celsius. So delta T temperature difference will be 8 degrees Kelvin. 1 degree Kelvin equals 1 degree Celsius. The difference is only in the origin, in the point where you start calculating, where the 0 is. But the amount of temperature in 1 degree Kelvin is the same as in 1 degree Celsius. So what we have here, grams will cancel, Kelvin will cancel, and what we obtain here, 1,000 times 8, that will be 8,000 calories. So this analysis, this is just a preliminary analysis. It's not a solution of the problem. This is a preliminary analysis which shows that in order to increase the temperature of all water up to 0 degrees Celsius, we need just 8,000 calories. But if all this water turns into ice this huge amount of heat energy will be released, 10 times larger than we need to increase the temperature of water. It's impossible to increase the temperature of water higher than 0 degrees because ice cannot exist at higher temperatures. The ice, if there is some ice, it can exist only below 0. So we may imagine this mixture of water and ice only at temperatures below 0 or 0 degrees Celsius. So no higher than 0 degrees. And in order to heat the water, we need 8,000 calories in order to heat it up to 0. But if all the water is turned into ice, then this amount of energy will be released 10 times larger than we need in order to heat the water. What does it mean? It means that not all the water will be turned into ice, but some small portion of it. Just some small portion of water will be turned into ice, and in this process, large amount of energy will be released, and the water and ice mixture will be increased to 0 degrees. For this purpose, we need this amount of energy, heat energy, but this amount of heat energy will be covered by the freezing water, by turning water into ice. So this preliminary analysis gives us the main conclusion, allows us to obtain the main conclusion that not all the water will be turned into ice. Just a small part of water will freeze in this process. If we throw a small piece of ice here, just a very small, tiny piece of ice, then some water will freeze, but a small portion of water. And all the water after this process will be heated up to 0 degrees. And at 0 degrees, the final state will be at 0 degrees. And at 0 degrees centigrade, we will have a mixture of ice and water. But all the water cannot be turned into ice in this process. Just a small part of water will freeze. That's the conclusion we come to after this analysis. And now we need to calculate the exact mass of ice after the process is concluded, after the thermal equilibrium is established inside this calorimeter. This is a calorimeter. A calorimeter is such a cavity which has thick walls impermeable to heat. So all the heat energy created here will remain here. It will not leak outside the walls of the calorimeter. Inside the calorimeter, the heat energy is conserved. So, how to calculate the mass, the final mass of ice? Well, actually, we have to use the same equations. We have to take into account that specific heat of ice, that is the amount of energy needed to increase the temperature of ice by 1 degree Celsius if we have 1 gram of ice. So this is specific heat is about 0.5 calories per gram Kelvin. That is the energy needed to increase the temperature of 1 gram of ice by 1 degree Kelvin. And the specific heat capacity of water is 1 calorie per gram Kelvin. So these are just constants: specific heat capacity of water, specific heat capacity of ice, and specific heat of ice melting. That's what we need. So suppose that 1 gram of ice has melted into water. Then this 1 gram will produce this amount of heat energy, Q calories of heat energy, if 1 gram of ice is melted into water. But if not 1 gram, but mi grams, then this will be the total energy released if some mass of water mi is is frozen, is turned into ice. This energy will be released if water is turned into ice. But if you want, if ice is melted if water is turned into ice, this energy will be released. But if ice is melted, then this energy will be consumed. The flow of energy is reverse, whether you have freezing or melting. The flow of energy is opposite. So this energy will be released if this mass of water is turned into ice. So if we have this final amount of ice, then such energy will be released. Where does this energy go? First of all, it will go to increase the temperature of ice itself. So it will be the specific heat of ice times the mass of ice, the same amount, times delta T, the temperature difference. And also, not only ice will be heated, but also water, the remaining part of water will be heated. And the remaining part of water is the initial total mass of water minus that mass of water which goes into ice. So the remaining part of water will be heated, and we need to multiply the mass of water by specific heat of water and by the same temperature difference. And from this equation, we must find the unknown quantity, which is this mass of ice here and here. This is easily done if we take all the terms containing mi in one part of the equation. We get qmi minus cimi delta t plus cw mi delta t, and that is equal to Cw, the original mass of water, delta T. Then from this equation we can easily obtain the mass of ice, which will be specific heat of water, capital M delta T, divided by Q minus specific heat of ice, delta T, plus specific heat of water, delta T. Let's calculate. We know all the quantities contained in this formula. So specific heat of water is 1 calorie. Mass is 1000 grams. Delta T is 8 degrees. Q approximately 80 calories per gram, minus specific heat of ice, approximately 0.5 times delta T, which is 8, plus specific heat of water, 1 times delta T, which is 8. All this gives what? 8,000. And here we have 8 times 0.5, this is 4. And this is just 8. So 80 minus 4 plus 8, that will be 84. Now let's check the units of measurement. Here, this is the amount of heat measured in calories per gram, and this is calories per gram and calories per gram Kelvin. So grams will cancel, and here we have calories per gram, and also calories per gram. Kelvin will cancel. So calories will cancel, and only grams will remain here as the unit of measurement. Only grams will be here. So what we have here is the number of grams. Well, if we divide 8,000 by 80, we obtain something like, well, exactly 100. But if we divide 8,000 by just slightly more than 80, then we will obtain slightly less than 100. It will be approximately 95 grams, slightly less than 100. By intuition, I give you the number 95. It may not be exactly true. It may be something like 96, maybe 94, but anything like that. Something like 95 grams, just a little bit less than 100 grams of water will turn into ice in this process. Something like a little bit less than 100 grams. So out of 1 liter of water, only 100 grams will turn into ice. That will be a small piece of ice, which is just 10% of mass of water will turn into ice, and the remaining 90% of mass of water, 90% will remain in liquid form. That will be pure water. But the temperature inside will be 0 degrees Celsius. At 0 degrees, we will have a piece of ice in thermal equilibrium with water and ice at 0 degrees Celsius. That will be the final state of mixture in this problem. Now I would like to discuss some more theoretical issues related to ideal gases. We were using this quantity of specific heat of ice and specific heat of water, and also specific heat of gases exist for each gas. Whatever you take, be it a hydrogen or oxygen, any gas, any ideal gas has its specific heat. So I would like to talk about specific heat. What is it and how to deal with it, and what quantities what values this quantity may take in different processes. So let's consider an ideal gas in some cylinder with a piston. So the gas is here, contained under the piston, and the volume of this gas is V, and the temperature is T, and the pressure is P, and we know that there is the equation of state of an ideal gas, and if we have only 1 mole of ideal gas, the equation of state will be that. 1 universal gas constant times absolute temperature. So we may change volume of this gas at our will, at our disposal. How at any function of time we may change, we may lift this piston, or we may push it down at whatever speed we want, and we may change volume arbitrarily, just as we wish. Also, we may change temperature. We may heat this amount of gas, or we may cool it by placing it in ice. If there is ice outside, then we may cool this gas. So we may change temperature and we may change volume arbitrarily, and therefore pressure will change according to this equation. So actually we may change any two parameters involved in this formula arbitrarily at our will. And it means that there are infinite number of possible processes with a gas. We may organize a process at constant volume when the piston is fixed at a particular position and the volume is kept constant. Yes, it's easy to organize such process. We may change temperature, and directly proportional to temperature, the pressure will change directly proportional to temperature. So we may organize a different sort of process if we arrange for a constant pressure. For example, we'll put here some weight and leave the piston as it is, allow it to go freely under some weight, so the pressure will be constant. And in this case, we may change temperature, and we will discover that the volume changes directly proportional to temperature. And also we may organize all other sorts of processes here. But whatever process is organized, no matter how much heat we supply here, and no matter how volume is changed, the law of conservation of energy will always hold. The law of conservation of energy related to thermodynamical processes is written in this way. The amount of heat energy supplied to the gas equals the amount of internal energy change, the change of internal energy of this gas, plus the work produced by this gas. The heat energy we have already discussed today, that the internal energy is proportional to change in temperature. The total internal energy of ideal gas is proportional to temperature. So the change in internal energy, delta U, is proportional to the change in temperature, and the coefficient of proportionality is just C, and by definition it's just the specific heat of ideal gas, the quantity with which we have worked in several problems. So this is the coefficient of proportionality, the specific heat of gas, or the specific heat of any substance, is by definition, is defined by this equation. The specific heat by definition is by definition, this equation here, this equation will hold only for the specific heat under the constant volume. And the general definition of specific heat is this one, the specific heat times the change in temperature. So by definition, in general case, the specific heat is defined as the ratio of the amount of heat supplied to the gas divided by the change in temperature. That is the definition of specific heat, the general definition of specific heat. If volume is kept constant, then no work is performed by gas, because work performed by gas is pressure times change in volume, delta V. We obtained this formula during one of the previous lectures. The work performed by gas equals the gas pressure times the change in volume. So if volume is constant, then the work is zero. And then in this case we have no second term in this equation. And in this case the specific heat under the constant volume, which is denoted by CV, will be equal to just delta U times delta T. and in this case it certainly will be equal to delta Q, because if the second term is 0, which is the case when the volume is constant, if no work is performed, then the change in internal energy equals the amount of heat energy supplied. Delta Q equals delta U. So delta Q equals delta U if the volume is constant. In this case, no work is performed. And in this case, we have this energy. We have this formula. But in general case, the specific heat is defined by this formula. So what if volume is constant, no work is performed, and in this case, specific heat can be specific heat of gas under constant volume can be assessed by the change in its total internal energy. But what if volume is not constant? What if we allow this piston to go up and down, well, say under constant pressure? Then some work may be performed by the gas. If the piston moves up, then the gas expanding will perform some work. We derived this formula earlier. And in this case, if pressure is constant, in this case, the law of conservation of energy, this one, will give us the following. First of all, according to definition of specific heat capacity, delta Q will be specific heat times delta T. That is from the definition of specific heat. But from the law of conservation of energy, delta Q will be equal to delta U plus P delta V. And delta U can be expressed using the specific heat under constant volume, CV delta T. And the second term can be expressed using the gas equation. So under constant pressure, P times delta V will be equal to gas constant delta T from the gas equation. So what we obtain here is CV, specific heat under constant volume, times delta T plus universal gas constant times delta T. Looking at this equation, I will take this term and these terms, and that will give me some relationship between the heat capacity in this process, in this particular process, and what kind of process we consider. We consider the process when pressure is constant, because under constant pressure we can use this expression for delta V. The delta V will be equal to R delta T under constant pressure. So such expression can be used only under constant pressure. So this is what we obtain here will be a particular quantity specific heat under constant pressure times delta T. This is not a general specific heat in any process, but the process is very definite. It's a peculiar process under constant pressure. So what we obtain here, if we consider this equation, we may cancel by delta T, and we obtain that specific heat under the condition of constant pressure equals the specific heat under the condition of constant volume plus universal gas constant. This is the relationship between specific heats of ideal gas, of 1 mole of ideal gas. We're talking about 1 mole because the number of moles here is unity. So for 1 mole of ideal gas, the specific heat under constant pressure is related in this way with the specific heat under constant volume. This formula was obtained by Julius Robert von Mayer, a German chemist and physicist in the first half of the 19th century. That is almost 200 years ago. Almost 200 years ago, Julius Robert von Mayer obtained this relationship. Let's now consider the gas processes on the PV diagram. We start from initial state of the gas, which has some certain pressure and some certain volume, initial pressure and initial volume, and we can conduct or perform different processes with the gas. For example, what is the process under constant volume? Volume is constant. It means that everything is changing, like pressure and temperature changing, but the volume remains the same. This is depicted on such diagram as a vertical line here. That is the process under constant volume, and in this process we will have heat capacity CV of ideal gas. What is the process under constant pressure? Well, it means that the pressure of the gas will remain constant while volume and temperature may change. So this will be isobaric process, and the heat capacity will be Cp in this process. But on this plane PV, we can draw infinite number of lines, not only vertical and horizontal. We can draw any infinite number of curves. For example, if temperature is constant, then we will have isothermal process, and under constant temperature it will be depicted like this curve. For this particular curve, PV is constant or temperature is constant, and this is called isothermal process, and the specific heat capacity under constant temperature, what is it? It will not be equal to Cp and not be equal to Cv. Let's look at the definition of heat capacity. If delta T, what is constant temperature? It's when delta T is 0. Temperature doesn't change. Delta T is 0. 0 in denominator means that this formula will give you infinite number, infinite, because we supply some heat energy to the gas in order to increase its temperature, and the temperature will be increased because volume increased. So we may supply some heat, or we may take some heat out of the gas. So delta Q is not 0, but delta T is 0 if temperature is constant. So we will have 0 in denominator, and that will produce infinite number. So heat capacity under constant temperature is infinite. Another possibility is to arrange such a process when delta Q is 0. Delta Q is the amount of heat exchanged with external surrounding media. This heat exchange may be 0 if we have a calorimeter with thick walls which are impermeable to heat, and then heat exchange will be 0. And any process inside the gas may be conducted under this condition by moving a piston. We may change volume and we may change temperature and change pressure if on condition that delta Q is 0, the exchange of heat energy with the external medium is 0. If such a process is called adiabatic process. If delta Q is 0, then such a process is adiabatic. What if we have adiabatic process? Delta Q is 0 and heat capacity by definition is delta Q over delta T. Delta T will not be 0. Temperature will somehow change, but 0 in nominator will produce 0 for delta 0 for heat capacity. How can we show this process here? Adiabatic process will go somewhat over the isothermal process. So for isothermal process, heat capacity under constant temperature is infinite, and for adiabatic process, heat capacity in adiabatic process is 0, and here it's infinite. So that's the picture of just a few possible processes in ideal gas. And in some processes, the heat capacity is 0, like an adiabatic process, because exchange of heat with external medium is 0. And in some processes, the heat capacity is infinite, because change in temperature is 0. And in some other processes, so here it's infinite, here it's 0. And in some other processes, heat capacity will have some definite value. But if we take the process under constant volume and the process under constant pressure, then the heat capacities will be related according to the formula of Robert Meyer. So what if we take some other process like this one? Well, the heat capacity will be some different. Well, it will not coincide with what we have discussed previously. That will be some different if we go along any other curve. If we go here or here, the heat capacity will take some different value. So it's a very important quantity which is tabulated, and it's given in physics handbooks and reference tables. But when you see the heat capacity in a reference book, you will actually see the heat capacity under constant volume. That's what is given. If you see some other heat capacity under constant pressure, then it's always written. They will always give you the information what heat capacity they give in a reference table. But usually you will see the heat capacity under constant volume. But you have to remember always that this heat capacity given in reference books is just valid for particular process with the ideal gas, very particular process. And there are infinite number of other processes when heat capacity will have absolute different values, including 0 and infinite number, infinitely great, infinitely large number. And finally, I would like to consider problem number 337. Problem number 337. To conclude this discussion of ideal gases. 337 reads, a closed vessel impermeable to heat contains ozone, which chemical formula is O3, 3 atoms of oxygen in one molecule, that is ozone at a temperature contains some amount, we don't know how much gas is there, but some amount of ozone at temperature 527 degrees Celsius, high temperature. After some time, the ozone is completely converted into oxygen. So ozone is converted into oxygen by itself. Oxygen contains 2 atoms in one molecule, 2 atoms of oxygen in one molecule. And what will be the temperature? We don't know. Find the temperature, find the increase of the pressure in the vessel. So what we have to find, the increase of the pressure, that is, that was some initial pressure for ozone and some final pressure for oxygen, and we have to find the change in pressure, that is P2 over P1. That is what we have to find. The increase of pressure in the vessel if the specific heat of formation of 1 gram molecule of ozone from oxygen is given. 1 gram molecule of O3, when 1 gram molecule of O3 is formed from oxygen, the specific heat of this process is given 34,000 calories for 1 gram molecule. So this is calories per gram, per mole. Assume that the heat capacity of 1 mole of oxygen at a constant volume is also given. Heat capacity of oxygen at a constant volume is known. It's 5 calories per mole and degree of Kelvin. So what happens here? What happens in this problem? What does it talk about? It says that there is some volume, some vessel with filled with ozone at a given temperature. And obviously the volume is somewhere in adiabatic container. It means that the heat energy is not exchanged with the outside bodies. The exchange of heat energy is 0, and all the heat energy contained here will remain here in this vessel. This is adiabatic walls of the vessel, and there is some ozone. And if there is some ozone, it's gas, and the gas has some pressure, and it has some volume, and it has some mass and some molar mass and temperature. So this gas certainly obeys the universal gas law. But in our particular case, the ozone was under pressure P1, the original pressure, and the molar mass of ozone differs from the molar mass of oxygen. Certainly, it's different. So we introduce the index here, mu sub 1. This is the molar mass of ozone. What is it? By the way, 3 atoms of oxygen in 1 molecule, and 1 oxygen atom is mole for 1 oxygen is 16. So times 3, it will be 48 grams. That is the mole, the amount of ozone which forms 1 mole. I remind you that 1 mole contains the Avogadro constant number of molecules. So gradually this ozone turns into oxygen. Somehow molecules of ozone lose 1 atom of oxygen, and these 3 atoms then combine to make molecules of oxygen, and this process goes by itself. And finally, what will be here? We will find oxygen here, and for oxygen, that was for ozone, and for oxygen the pressure will be different, and we have to find it. The pressure will be different, but the volume will be the same. The volume is the same. It says nothing about the change in volume. Yes, the volume is the same. The mass of substance inside, the same. We don't lose molecules, we don't add gas here, and we don't lose gas. So the mass of gas here is the same. Whatever chemical conversion takes place inside this vessel, the mass will remain the same. But the molar mass will be different. Now it will be mu sub 2. Let me denote the molar mass of oxygen. That will be 32 grams. And the universal gas constant is the same, and the temperature will certainly be different. So that was temperature 1, and here we have temperature 2. Temperature will change, certainly, because some heat energy is released here. Well, what is necessary to understand when we consider such process is that when 2 atoms stick to form a molecule, why does it happen? Only because atoms interact. Only through interaction they form molecule. And if this molecule is stable, then the interaction is of attraction kind. The 2 atoms attract to each other, like 2 atoms of oxygen. They attract to form the molecule of oxygen O sub 2. And this molecule is stable. It's not easy to separate the 2 atoms. In order to separate them, you have to apply some energy and perform some work in order to separate atoms and move it apart from one another, because they are attracted to one another. So this attraction may be depicted if I introduce the potential energy of interaction of 2 atoms, the potential energy of interaction, and that will be the distance between the 2 atoms. Then the potential energy of interaction between 2 atoms usually has this form. When atoms are apart from one another, there is no interaction or very, very small interaction. When atoms come closer, they are attracted, and that means that the atoms fall into this potential well, which describes the energy of interaction, potential energy of interaction. But when the distance is smaller, the atoms are repulsed from one another, and so they meet this potential wall. And they live here, the atoms live here and vibrate about some position of equilibrium. And so this may be the distance between the 2 atoms in a molecule of oxygen. That's what happens from most general physical understanding, physical considerations, when atoms form a molecule. Originally, atoms had 0 energy, but when they form a molecule, the energy is less than 0. The energy is negative. And in order to separate the atoms, you have to perform some positive work in order to separate them and move them at a larger distance. So when the atoms form molecule, they must lose this energy. They must give this energy to some other bodies, external bodies. Most commonly, this happens when they emit a quantum of light, quantum of electromagnetic radiation. But sometimes this energy is given in collision to some third atom or third molecule. Sometimes this energy is given in collision to some other object, like other molecule. But anyway, the 2 atoms of oxygen must lose some energy in order to form a molecule of oxygen. And when another atom of oxygen comes here to form the molecule of ozone, Why it happens? Because the atom of oxygen will be attracted to the molecule of oxygen to form a new molecule of ozone, but this attraction will be much smaller. And if we put it here, the attraction, the potential energy of interaction between atom of oxygen and molecule of oxygen, that will be practically the same, but the energy will be much smaller because it's much easier to separate and to disintegrate the molecule of ozone. So this will be the energy of the molecule of ozone. It will be much smaller than the energy of bond energy in the molecule of oxygen. So in order to separate one atom of oxygen from the molecule of ozone, you have to perform this amount of work. You have to supply this amount of energy. This energy will be absorbed, and then a single atom will fly somewhere, and another single atom will be found from a similar process with another molecule, and two atoms of oxygen will form a molecule of oxygen, and the molecule of oxygen, when it forms, will release much more energy. So some energy is taken to disintegrate the molecule of oxygen, some small energy, but larger energy will be released when the molecule of oxygen is formed out of two atoms. So all this process consists when the ozone separates. First you have to supply some energy, and then more energy will be released. Where do we take this energy which is needed to disintegrate the molecule of ozone? Where this energy comes from? From collisions, from kinetic energy of collisions of molecules. So some energy will be taken, and then much more energy will be released when the molecule of oxygen is formed out of two atoms of oxygen. So this ozone molecule refers to this, to the red graph of potential energy versus distance, and this graph refers to the molecule of oxygen. Here we have small energy, here we have much larger energy. So the process of disintegration of ozone into oxygen requires, first of all, some energy which is taken from collisions, and then much more energy is released. Where does this energy go which is released if we are in a closed volume in adiabatic walls? This energy can go nowhere but to heating the gas. So if the gas is heated, all the released energy will go to increase its temperature. And we know that when one mole of ozone So if 1 mole of ozone is disintegrated, then this amount of energy is released per 1 mole of ozone, So this energy is released, and how much energy will we have? We will have this energy per mole by the number of moles of ozone. This is the number of moles of ozone. By the number of moles, that is m over mu1. The energy released per 1 mole of gas times the number of moles of gas. That will be the total energy released when all the ozone is turned into oxygen. And where does this energy go? Finally, this energy is absorbed by the gas oxygen in order to increase its temperature. So the total amount of gas will be the same, the total mass of gas, but the molar mass will be different, and that will be the number of moles of oxygen. That is the number of moles of ozone, and that is the number of moles of oxygen, times specific heat capacity of oxygen per mole, times the temperature difference, which will be T2. The temperature, the final temperature will be larger because the energy is released here. The energy, heat energy, is produced in this volume. So T2 minus T1. That's the energy balance equation, which describes the processes that take place here inside this vessel. This is the energy released because the ozone separates and combines, and new atoms, released atoms, combine to form oxygen. This is the energy released, and this released energy goes to increase the temperature of what? Final gas, oxygen. So we have to take the number of moles of oxygen and molar heat capacity. Molar heat capacity differs from the mass heat capacity by the fact that it's calculated for 1 mole rather than for 1 gram or for 1 kilogram. It's calculated for 1 mole. So that's the energy balance equation for this particular process. And what do we have to find? We have to find pressure 2 over pressure 1. In order to find this relationship between pressures, we must divide second equation by the first equation here. Let's divide second equation by the first equation. That will give us P2 over P1. Volume will cancel, the mass will cancel, and what we will have if we divide the second equation, mu2 will be in denominator and mu1 will go to the nominator, and universal gas constant will cancel, and what will remain here, T2 over T1. That's the result of division of the second equation by the first equation. Volume cancels, mass cancels, universal gas constant cancels. That's what remains. So in order to calculate this formula, we must know the result of division of mu1 by mu2, which is very simple. Mu1 divided by mu2 can easily be calculated. It is just 3 over 2. So this quantity is known. And what we need to calculate is the relationship between temperatures. How can we do it? Let's consider this equation. Certainly the mass here can be cancelled in this equation. If we divide this equation by T1 in order to obtain T2 over T1, let's divide this equation by T1. It seems reasonable because T1 is the initial temperature which is given. By the way, it's given in Celsius, but the temperature here is given in Kelvin. This is the absolute temperature. So we need to transform Celsius temperature to Kelvin. A Kelvin temperature will be a Celsius temperature plus 273 degrees. So in Kelvin, this will be 800 degrees Kelvin. Yes, 800 degrees exactly. 27 plus 73. So the initial temperature is given 800 degrees absolute temperature of the gas initially. So if we divide this equation by T1, we obtain something like that. T2 over T1 minus T1 divided by T1 is 1 times C divided by mu2, but I will take these two quantities to another part of equation, and that will give me Q. That will give me Q divided by C, and here I will have mu1 and mu2. Mu2 will go to nominator. That's it. And I divided everything by T1, so T1 must be here. Is everything correct? Q over C, mu2 over mu1 divided by T1. That's it. So from here I can find the relationship between temperatures. The relationship T2 over T1 is what? 1 plus this quantity. And I will not even calculate it. I will not even calculate it. I will put it immediately here. So what I have here is mu1 over mu2. T1 over T2 is 1 plus Q over C. I take this expression mu2 over mu1, mu2 over mu1, and also 1 over T1. So when I open this round brackets, I will have mu1 over mu2 plus Q over C temperature T1, and here all mu's will cancel. That's the simple formula, which is easy to calculate. What is mu1 over mu2? We already know. This is 3 over 2 plus, what is Q? It's 34,000 calories per mole. What is C? C is given as 5. Note that this is C under constant volume. Exactly what we need in this problem. The volume of vessel remains constant in all this, during all this process. So C is 5 calories per volume, and T1 is known 800 kelvins. 800 kelvins. So we need just to calculate it. We need to cancel two zeros, and 340 divided by 5. 340 divided by 5 will give me 68, and divided by 8, and that will be 3 over 2 plus, what is the result? That will be 8 1/2. So what we have here is just 10. So the final pressure in this process will be 10 times larger than the initial pressure. That's the answer to this problem. We need to find the relationship between pressures, and we found it during the process of transformation of ozone into oxygen inside the constant volume. If the initial temperature was 800 degrees Kelvin, then the final pressure will be 10 times larger than the initial pressure. Note one interesting thing. We are not given the amount of gas. The mass is not given. We don't know what is mass. And we don't know what is the initial pressure and what is the final pressure. We know nothing about it. Whatever mass you take and whatever the initial pressure you take, the pressure increase will be tenfold. The final pressure will be tenfold the initial pressure. That's the answer to this problem. So on this point, let me finish our lecture, and all my students tomorrow night will receive information about the written test that will be given to you on Saturday at 10 o'clock in the morning Moscow time.